Welcome to our quantum deep dive. Today, we're taking on, well, a truly mind-bending topic. It's this fascinating intersection of classical AI and the quantum realm. We're going to explore what are called hybrid quantum-classical Bayesian networks, HQCBNs, you could say. And our insights today, they're drawn from a really compelling essay by Yorgo Schneepat. Our mission here is to give you a kind of shortcut, to really understanding how these cutting-edge models could fundamentally change how we process information, how we make decisions in, well, an increasingly complex world. It's important stuff.
Indeed, it absolutely is. It's really about merging two powerful but quite distinct computational paradigms. We'll be breaking down how these hybrid networks could maybe address some of the fundamental limitations we see in current AI systems.
Okay, so let's start with the big picture then, the why. Why do we even need HQCBNs? What problem are they actually trying to solve?
Well, in artificial intelligence, especially when you're dealing with uncertainty, with decision-making, probabilistic models are absolutely central. Think about real-world data. I mean, it's rarely perfect, as it is often incomplete, it's noisy, maybe only partially available. So a purely deterministic approach, just yes or no, it quickly hits its limits there. It just can't handle that ambiguity well.
Right. So instead of a simple yes or no, you need a system that can kind of weigh the possibilities, understand all the maybes and the what ifs, quantify likelihood.
Precisely, yeah. Probabilistic methods allow us to embrace that uncertainty. They give us robust predictions based on probability distributions.
Okay.
And a prominent example, really foundational here, is Bayesian networks. They represent these distributions using a directed acyclic graph, a DAG.
Okay. And the mathematical engine behind this, what's the core principle that lets them learn and adapt?
It all comes back to Bayes' rule. It's this really powerful mathematical idea. It lets us update our beliefs about something, a hypothesis, as new evidence comes in. It's absolutely essential for inference, for allowing us to integrate new information and constantly refine our probability distributions. Think of it like a continuous learning loop for probabilities.
Okay, now here's where it gets really interesting, I think. With data analysis becoming so much more complex, the sheer volume of information exploding, the need for more efficient probabilistic modeling grows a lot. And that's where, well, the mind-bending world of quantum mechanics enters the picture. It promises a way to maybe leapfrog some of these current limitations.
Yes, what's truly fascinating here is that quantum mechanics, with its inherent parallelism, things like superposition and entanglement, it has the potential to significantly accelerate these probabilistic computations. It really opens doors that are, well, currently closed to classical systems just because of the sheer computational load.
But hold on a sec. We're not just swapping classical for quantum entirely, are we? I mean, current quantum computers, they have some pretty significant limitations.
Exactly. That's a crucial point. While quantum computers theoretically offer immense advantages, today's machines, well, they're still pretty sensitive to errors. They have a limited number of qubits, and they face physical constraints like decoherence, where the quantum state just kind of fades away. So this raises a really important question. How do we actually harness their power now? Despite these current limitations.
So the practical approach, the sensible thing, is a hybrid model.
Okay.
What would that actually look like in the context of these HQCBNs? How do the classical and quantum parts work together?
Right. So in a hybrid quantum classical Bayesian network, we could use a classical system for the tasks it excels at, like, say, calculating specific conditional probabilities.
Yeah.
While the quantum system, maybe it generates parallel samples much more efficiently because that's its strength. Or we could leverage specific quantum algorithms like Rover's search for faster inference, speeding up the search for the most probable states in the network. And if you connect this to the bigger picture, these kinds of approaches could drastically reduce the computational burden for really massive probabilistic models that could make real-time complex calculations feasible in fields like medical diagnoses, financial market analysis, advanced AI. It's quite revolutionary potential.
All right, let's drill down into the classical side first, just for a moment. For listeners who might be familiar but maybe want a quick refresher, what exactly is a Bayesian network and how does it generally work?
Sure. So Bayesian networks are a class of probabilistic graphical models. They represent conditional dependencies between variables explicitly in the form of a directed acyclic graph, or GADEGE, as we mentioned.
Okay.
So each network has nodes. These represent random variables. Then you have edges, which show the probabilistic dependencies between these variables. And finally, conditional probability distributions, which define the probabilities for each variable given its parent nodes in the graph.
Okay. Can you maybe give us a quick relatable example so we can really picture it?
Certainly, yeah. Imagine a simple medical diagnosis system. You might have a disease node, and that node influences, say, a fever node and a cough node. Now, the crucial part is that fever and cough might appear dependent on each other, but perhaps only through the disease. Once you know whether the disease is present or not, knowing about fever tells you nothing new about cough, and vice versa. They become conditionally independent. And this structure, this graph, allows the entire probability distribution of the whole network to be calculated really efficiently using the chain rule of probability.
So what are the big benefits then? Why are they so widely used in AI and other fields? What makes them so useful classically?
Well, their main advantages are, first, efficiency in calculating probabilities, because they factorize these complex joint probabilities into smaller, manageable parts based on the graph structure. They also offer great flexibility. It's relatively easy to expand the model, add new variables, new connections, without having to rebuild everything from scratch. And crucially, they have excellent interpretability. Because the relationships, the dependencies are explicitly shown in the graph, it makes it easier for humans to understand the model's logic. You can kind of read the model.
But as you mentioned, they do have their limits, especially with complex models. What are the fundamental challenges that have pushed people to look for something new, like quantum?
Yeah, despite their strengths, classical Bayesian networks can become very computationally intensive, especially when the number of variables grows or the dependencies get really complicated. What's the sort of brick wall that classical systems hit when these networks become very large?
It's that exponential growth thing, right? That sounds like a massive bottleneck.
It really is. For n variables, a full probability table could need 2n entries. That leads to exponential growth in memory needs.
Mm-hmm.
And the calculation of probabilities, what we call inference, asking the network questions like, what's the probability of this disease given these symptoms, that can also be NP hard.
Mm-hmm.
Computationally, very, very hard, especially if you have long chains of dependencies in your graph. This makes exact calculation quickly impractical for many real-world scenarios. It's like trying to compute every possible chess move. It just blows up.
So powerful tools, but they get bogged down. Too much data, too many connections, and they just can't keep up.
Yes, exactly. And there's also the difficulty sometimes in modeling truly complex real-world relationships. The assumptions of conditional independence might not always hold as cleanly as the neat graph diagram suggests. And learning the actual probability numbers, the distributions, from data. That either demands massive data sets, which aren't always available, or requires very sophisticated optimization algorithms, which are themselves computationally expensive. So ultimately, classical hardware just hits its limits when these networks get really big. And that's common in cutting-edge AI research where you're trying to build more nuanced, more accurate models.
So this really sets the stage. It raises the important question, how do we break through these classical barriers? How do we move beyond these computational walls? That's precisely where things get really interesting, where the game changes. With the, mind-bending possibilities of quantum mechanics, how do these strange quantum principles actually help with data processing, and specifically with Bayesian networks? It feels like a huge leap from classical probability.
It is a leap, but a potentially powerful one. What's fascinating is that quantum mechanics fundamentally shifts how we think about information itself. Unlike classical physics, which is deterministic, cause and effect, precise predictions, quantum mechanics is inherently based on probabilities and state superpositions. And that probabilistic nature actually aligns quite nicely with the core ideas of Bayesian networks.
Okay, so what are the key principles then, the things that make quantum computers fundamentally different from the classical ones we use every day?
Right. Well, first off, qubits. A classical bit is simple. It's either 0 or 1. That's it. A qubit, though, can be in a superposition of both 0 and 1 simultaneously. You can think of it like having a dimmer switch instead of a simple on-off switch. It can be partly 0 and partly 1 at the same time. It's represented mathematically with amplitudes, complex numbers, where the square of the amplitude gives a probability of measuring 0 or 1 when you finally look at it.
So a qubit isn't just 0 or 1, but this weighted possibility of both until you measure it. How does that directly unlock new computational power for something like a Bayesian network?
That's the absolute key. This superposition allows for what we call exponential parallelization. A system with just n qubits can simultaneously represent and process information about 2ln states. So a quantum computer can perform operations on this huge number of states all at once, which can drastically increase computational throughput compared to classical systems that have to process things one state after another.
That's still mind-boggling every time I hear it. Okay, what about entanglement? That's another one of those quantum concepts that sounds like science fiction.
It does, doesn't it?
Yeah.
Entanglement is another fundamental and frankly weird property. Two or more qubits can become linked, correlated in such a deep way that measuring the state of one instantly influences the state of the other, no matter how far apart they are. This profound sort of non-local connection is a core resource for quantum computation. It allows for correlations that classical systems just can't replicate easily, which can be useful for representing complex dependencies in probabilistic models.
And then there's interference. How does that play a computational role?
Right? Quantum interference. This allows the probability amplitudes associated with different computational paths to either reinforce each other, making a particular outcome more likely, or cancel each other out, making other outcomes less likely. And quantum algorithms cleverly exploit this interference to amplify the probability of getting the correct answer while diminishing the probability of incorrect ones. It's like guiding the computation towards the desired solution much faster.
Okay, so putting this all together, superposition, entanglement, interference, what does it all mean for Bayesian networks? How do these quantum properties translate into actual tangible benefits for those really challenging probabilistic calculations we talked about?
Well, the combination offers several potentially powerful synergies. For instance, quantum computers could generate parallel samples from probabilistic models much faster, drastically reducing the computation time needed for inference, especially approximate inference methods. They can also provide improved optimization algorithms. Finding the most probable state or configuration in a large Bayesian network can be framed as an optimization problem, and quantum algorithms might solve these much faster than traditional methods.
You mentioned specific quantum algorithms earlier, like Shor's for factoring. How does something like Grover's algorithm apply here specifically to Bayesian networks?
Grover's algorithm is a really relevant one here. It's famous for speeding up the search of an unsorted database. Classically, that takes O(n) time on average. Quantumly, Grover's does it in O(n). Now, you can frame certain problems in Bayesian networks, like finding the most probable configuration of variables as a search problem. So Grover's algorithm can potentially be used to find that most probable configuration much faster than classical search methods. We can also potentially use things like quantum Monte Carlo algorithms for more efficient probabilistic calculations in general, and quantum-enhanced optimization techniques for tuning network parameters.
So the advantages seem clear on paper: exponential parallelization, faster search and optimization, entirely new computational pathways. But what about the challenges? What are the practical hurdles facing quantum computing today that stop us from just using it for everything?
That's the reality check, isn't it? The main challenges are significant. First, decoherence. Qubits are incredibly fragile and sensitive to environmental noise vibrations, temperature fluctuations, stray magnetic fields. This noise causes them to lose their quantum properties, their superposition and entanglement, which leads to errors. Then there's error correction. Because of decoherence, we need robust ways to detect and correct errors, and building fault-tolerant quantum computers that can do this effectively is a massive engineering challenge. Also, current quantum computers still have a fairly limited number of qubits. We're talking tens or hundreds, maybe thousands soon, but not the millions we might eventually need for really complex problems. They aren't yet scalable enough for truly large-scale models. And this is precisely why hybrid algorithms are so important right now. They try to bridge that gap, using classical computers for what they're good at and these noisy intermediate-scale quantum NICQ devices for specific tasks where they might offer an advantage even with their limitations. But despite these hurdles, it's important to note that initial practical implementations, proof-of-concept studies of quantum-assisted Bayesian networks are already happening and showing some very promising results. It signals the potential, even if we're not fully there yet.
Okay, so we understand the classical side, its strengths and weaknesses, and we understand the quantum side, its potential and its current challenges. Now, how do we actually combine them? How do we build these hybrid quantum classical Bayesian networks? What does a hybrid system actually mean in practice for something like a Bayesian network?
Right. A hybrid system in this context is really about intelligently combining the strengths of both worlds. Classical computers, as we know, excel at precise, deterministic calculations, controlling complex workflows, storing large amounts of conventional data. Quantum computers, on the other hand, with their inherent parallelism and probabilistic nature, seem better suited for specific, often computationally hard, tasks like high-dimensional optimization, complex sampling, or simulating quantum systems themselves. So in HQCBNs, this means both classical and quantum processors are used, but for different complementary parts of the overall computation. They work together.
Okay, so what are the specific tasks that the quantum part typically handles in this hybrid setup? How does it contribute its unique capabilities?
Well, the quantum component could perform efficient sampling from complex probability distributions, swiftly exploring large state spaces that would just be intractable for classical computers. It could also help optimize the network structure itself, maybe using algorithms like Grover's, as we discussed, to find the best configuration of dependencies between variables. And it could facilitate parallel inference processes, maybe by preparing quantum states that represent parts of the probability distribution and then manipulating them simultaneously, which could significantly speed up finding answers to probabilistic queries.
That makes sense. It's about leveraging the right tool for the right job. Are there different ways this integration can be structured? Different architectural models, perhaps?
Yes. The essay by Schneppat outlines three main approaches, three ways you could structure this hybrid integration. First, you could have classical nodes with quantum calculations. In this model, the Bayesian network itself, its structure, remains classical. You draw it just like you normally would. But specific, computationally intensive parts, maybe calculating a particularly nasty conditional probability table, or performing an optimization step during learning, are offloaded to a quantum computer, a QPU. This seems ideal for maybe accelerating parameter optimization or doing efficient sampling for a specific part of the network without changing the overall classical framework too much.
Okay, that sounds like maybe the most straightforward approach to start with. What's the second way? How does that differ?
The second approach is kind of the inverse. Quantum nodes with classical control. In this model, certain nodes within the Bayesian network are actually implemented as quantum registers collections of qubits. These quantum nodes would store and process probability distributions directly using quantum states, using superposition. This could allow for much more efficient storage of very large probability distributions, since Heugwitz can store 2n amplitudes. And it might allow leveraging quantum entanglement to model subtle, hidden dependencies between variables that might be missed in a purely classical graph. The classical computer would still manage the overall process, controlling these quantum nodes.
Interesting. So the nodes themselves become quantum. And the third approach, the most integrated one.
Right. The third is fully hybrid networks. As the name suggests, these would integrate both classical and quantum nodes seamlessly within the same network structure. You'd have classical nodes handling maybe deterministic calculations or simpler probabilities, while quantum nodes tackle the really complex probabilistic parts, efficiently executing those calculations using quantum parallelism. This approach aims to maximize the utilization of quantum parallelism wherever it's most beneficial within the network's computation. The primary drawback here, of course, is the current state of quantum hardware. Given the limited qubit counts and their fragility, implementing these fully integrated hybrid models at any significant scale is really difficult right now. It's more of a future goal.
You mentioned earlier how quantum computing accelerates inference. Can you maybe elaborate a bit more on how it does that? What's the actual mechanism for speeding up those calculations that are often notoriously slow in classical Bayesian networks?
Sure. So in classical systems, inference finding the probability of some variables given others often involves computationally heavy methods. Things like variable elimination, which can have exponential complexity, or approximate methods like Gibbs sampling or Markov chain Monte Carlo, MCMC, which can be slow to converge. Quantum computers offer a few potential ways to speed this up. One is by parallelizing the representation of probability distributions using superposition, as we discussed. A quantum state can inherently encode vast amounts of probabilistic information. Another is through quantum-assisted sampling. Quantum algorithms might be able to generate samples from complex high-dimensional probability distributions much faster or more effectively than classical random sampling methods, especially for finding high-probability states. And then there are specific quantum inference algorithms. Some research explores using techniques like amplitude amplification, related to Grover's algorithm, or phase estimation to directly calculate marginal probabilities or perform other inference tasks potentially faster. The essay specifically mentions an idea called quantum belief propagation, which tries to use quantum interference effects to speed up how probability information propagates through the network graph.
Looking at the specific tools, the algorithms being used in these hybrid systems, what stands out to you as particularly key or promising?
Well, Grover's algorithm for that quadratic speedup in probabilistic search is definitely a key one people are exploring. Finding the most likely explanation, the MAP estimate, is often a search problem. Quantum Monte Carlo sampling methods are also very relevant. If quantum computers can generate samples more efficiently, it significantly boosts many approximate inference techniques widely used today. And then there are quantum variational algorithms, or VQAs. These are particularly interesting for the current NISQ era. VQAs use a quantum computer to prepare a parameterized quantum state and measure it, but they use a classical computer to optimize the parameters of that state. It's a hybrid loop. They offer a flexible way to potentially model complex probability distributions more efficiently than classical methods, even on today's noisy quantum hardware. They're a very active area of research.
This all sounds incredibly advanced, maybe even a bit futuristic. But are there actual tools, software frameworks available today for developers or researchers who want to start experimenting with HQCBNs? Can people actually try this stuff out?
Oh, absolutely. Things are moving quite fast in that regard. The essay highlights several crucial software frameworks that are already available and being actively developed. For instance, IBM has Qiskit. It's a very popular open source framework that explicitly supports building and running hybrid algorithms, including things like variational quantum circuits. Google has Cirq, which is also open source and particularly optimized for near-term NISQ devices. And crucially, Cirq integrates with TensorFlow Quantum, or TFQ. TFQ itself is a major development. It extends the popular machine learning library TensorFlow, specifically for quantum machine learning, allowing you to build models that combine classical neural networks with quantum circuits run on simulators or real hardware. That's perfect for hybrid approaches. And then you have cloud platforms like Amazon Braket. Braket provides a sort of unified interface to access quantum hardware from different providers, Rigetti, IonQ, Oxford Quantum Circuits, plus simulators, making it easier to experiment with different quantum technologies within a hybrid workflow.
Okay, so the tools are emerging. It sounds like it's a genuinely promising method for accelerating probabilistic modeling. It's flexible in how you can integrate the quantum parts, but it still faces those real hardware limitations and the challenges of error-prone quantum processors. It's truly a field in its early but very exciting stages. All right, let's shift gears a bit and talk about the real-world impact. Where can we expect to see these hybrid quantum-classical Bayesian networks actually making a tangible difference? Maybe not tomorrow, but in the near future.
Yeah, that's the crucial question, isn't it? HQCBNs really have the potential to revolutionize how we optimize large probabilistic systems. We've talked about how classical methods often struggle with that exponential growth in calculations, making many problems intractable. But quantum-assisted optimization, even with the quadratic speedup from something like Grover's, can provide really significant performance boosts. It could turn problems that are currently impossible to solve optimally into ones that are merely difficult or even efficiently solvable.
Can you give us some concrete examples? Where would this optimization power be most beneficial?
Sure. Think about route optimization. Things like flight planning for an airline, or complex logistics for a delivery company with a huge fleet of vehicles operating in a large network. These are massive optimization problems under uncertainty. HQCBNs could potentially find better, more optimal solutions much faster than classical algorithms can today. The same applies to managing large utility networks, power grids, water distribution systems, telecommunications networks. Probabilistic models are already used here for things like predicting faults or planning maintenance schedules. HQCBNs could make these predictions more accurate or allow for much larger, more detailed models, leading to more efficient and reliable infrastructure management. That speedup is potentially a game changer for searching through the vast space of possibilities in these networks.
Interesting. What about in medicine? That seems like a field where more accurate, faster, probabilistic modeling could have a huge impact on people's lives.
Absolutely. Medical diagnosis is a prime example. Doctors often implicitly use Bayesian reasoning, weighing symptoms and test results. Formal Bayesian networks are already used to model complex symptom-disease relationships. With HQCBNs, we could potentially see significantly improved diagnostic accuracy and maybe speed. For instance, quantum-assisted sampling could help explore the complex probability distributions involved in rare diseases or conditions, with many interacting factors, leading to faster or more reliable diagnoses. And looking further ahead, you can imagine using HQCBNs for personalized medicine, processing large amounts of genetic data, clinical trial results, patient history, all with inherent uncertainties to optimize treatment plans for individual patients. Imagine a hybrid system improving cancer diagnosis not just by detecting it, but by using quantum optimization to analyze vast data sets to predict the best possible therapy for that specific person.
Wow. Okay. And the world of finance. That's another area defined by massive data volumes, huge uncertainty, and where even small computational advantages can mean enormous returns.
Exactly. Finance is definitely a prime candidate. Think about risk assessment, modeling the complex interplay of market factors to predict potential losses, Or portfolio optimization, finding the best mix of assets to balance risk and return, which is a notoriously hard optimization problem. Or fraud detection, identifying suspicious patterns in vast streams of financial transactions. HQCBNs could potentially lead to more precise risk evaluations by handling more complex dependency models, faster trading strategies enabled by quicker inference processes, and perhaps quicker, more accurate identification of fraudulent activities through quantum-assisted pattern recognition on a scale that's currently difficult. And this isn't just theoretical. IBM, for instance, has published work using their quantum computing platform to test hybrid algorithms, specifically for portfolio optimization problems, showing that real-world exploration is underway.
This really sounds like it could be a massive leap for artificial intelligence itself, kind of fundamentally changing how AI works, beyond just these specific applications.
I think so, yes. Classical machine learning models, especially deep neural networks, often hit scaling issues with very large data sets or extremely complex architectures. Training them can take days or weeks on huge classical clusters. HQCBNs, or more broadly hybrid quantum classical machine learning approaches, could bring several benefits. Accelerated probability calculations could be integrated into certain types of neural networks. Optimized hyperparameter searches finding the best settings for a machine learning model could potentially be sped up using techniques like variational quantum circuits. And more efficient pattern recognition or feature extraction from high-dimensional data might become possible. Google's TensorFlow Quantum, which we mentioned, is a concrete example of this direction-building tools to combine classical neural networks with quantum computations for potentially enhanced performance. This could really revolutionize areas like speech recognition, complex image processing, natural language understanding, and definitely probabilistic decision-making in systems like autonomous vehicles, making them potentially more robust and capable in uncertain environments.
It all sounds incredibly promising, almost like a guaranteed future just around the corner. But let's bring it back to Earth for a moment. What are the major challenges still standing in the way of bringing this to widespread practical implementation? What are the hurdles we still need to overcome?
Right, it's crucial to be realistic. This raises the important question of roadblocks, and they are significant. First and foremost, the current limitations of quantum hardware. We've touched on this relatively few qubits, high error rates due to decoherence. Today's NISQ devices are powerful for certain tasks, but they're not yet the universal fault-tolerant machines envisioned for the long term. Second, integrating these fundamentally different quantum systems with existing classical software stacks and workflows poses a major technical challenge. It requires new programming models, new expertise. Then there's the ongoing scientific and engineering challenge of achieving fault tolerance, building quantum computers that can reliably correct their own errors. That's likely years, maybe decades away for large scales. The implementation costs are also very high currently. Building and operating quantum computers is incredibly expensive. And finally, there's a distinct lack of expert knowledge. This is a truly interdisciplinary field requiring expertise in quantum physics, computer science, AI, and specific application domains. Finding people with that breadth of knowledge is difficult, which slows down practical adoption, and it requires significant investment in new educational initiatives.
So, a lot of hurdles still. Given all that, what does this realistically mean for the future? Where do we see this heading?
Despite the challenges, the future potential remains vast. I think we can reasonably expect continuous advancements in quantum hardware, more qubits, lower error rates, better connectivity. That progress seems steady, even if the timeline is uncertain. We'll also likely see improved algorithms specifically designed for these hybrid Bayesian networks and other hybrid quantum classical tasks, algorithms that are more resilient to noise or make better use of limited qubits. And as the hardware and algorithms improve, we'll likely see a broader application across more interdisciplinary fields. Think genomics, where modeling complex gene interactions is crucial. Meteorology, for improved probabilistic weather forecasting, incorporating more data and physics. Autonomous systems making decisions under uncertainty. These fields really highlight HQCBNs and hybrid approaches generally as potentially a key enabling technology for the next generation of AI.
So this could genuinely, fundamentally change how AI models are trained and optimized in the long run. Not just an incremental improvement, but maybe a true paradigm shift.
Precisely. That's the exciting prospect. We're potentially looking at significantly faster probability inference, which could enable real-time AI models for applications where that's currently impossible. Think complex control systems or instantaneous financial modeling. It promises potentially improved learning algorithms for machine learning, maybe allowing neural networks or other models to be trained more efficiently, perhaps on less data, or to achieve higher accuracy. And overall, it could lead to better modeling of uncertain data, allowing AI systems to make more robust, more reliable decisions when faced with the complex, ambiguous, probabilistic nature of the real world. And the emergence of these new quantum AI frameworks, like TensorFlow Quantum and Penny Lane and others, shows that the software infrastructure is being built now to support this future. So yes, while there's still a long road ahead, these hybrid quantum classical systems really could fundamentally transform AI development in the long term, pushing the boundaries of what's computationally possible.
And that brings us to the end of our deep dive into hybrid quantum classical Bayesian networks. It's definitely a complex topic, but wow, an incredibly exciting field too. It really shows us how the future of AI might just combine the best of both classical and quantum worlds to tackle problems that are currently, well, beyond our reach. We really appreciate you joining us on this journey today to unpack these fascinating and sometimes tricky concepts.
Yes, and we hope this deep dive, drawing on Jorgo Schneppat's insightful work, has given you a clear understanding of this potentially revolutionary technology and how it might shape the future of information processing and AI.
If you're curious, if you want to dive even deeper into the details, you can definitely find more information and continue your exploration on the author's website. That's schneppat.de. Thank you so much for joining us for this deep dive. Until next time, keep learning, keep exploring.